All right, guys. So this video is just going to go over just a quick lesson in VSEPR theory, valence shell electron pair repulsion theory, and I just want to use this to kind of distinguish between what we call VSEPR geometry and VSEPR shape. So we kind of, whenever I ask you, what's going on around the molecule, what shape is it? I'm looking for the VSEPR theory shape. It's a more specific way to describe the molecule. But if you ever, Google VSEPR theory or anything, you're going to see there is a difference. There's the geometry of the molecule, and then there's the shape of the molecule. Now, on the AP exam, they'll most likely ask you for the shape, if it's most of the time. And so you can never go wrong with shape. So if I ask you the VSEPR theory geometry, and the geometry is trigonal bipyramidal, or the geometry is trigonal bipyramidal, but the shape is seesaw, and I ask you for the geometry and you say seesaw, which is the shape, not the geometry, you would get full credit. But if I asked for the shape and you just gave me the geometry and they weren't the same thing, sometimes it's the same thing, then that's when you would go incorrect. So you can always, you can never go wrong with giving the shape. But there is kind of a difference, okay? So I just want to distinguish between, VSEPR theory geometry versus VSEPR theory shape, and then just show you a couple examples. So yeah, okay, so, and this is all assuming that you know the structure of the molecule, so you're able to draw the dot structure. So if you can't draw dot structures yet, make sure you go back and watch the other videos, okay? So, right, or just, pay attention in class. All right, so, so VSEPR theory shape versus geometry versus shape. Okay, so geometry is the more broad term, and so within each geometry, we have different shapes. So the same geometry can have different shapes, and it all depends on the number and types of domains you have. So let's define a domain. So first off, let's make sure we understand. If I'm trying to figure out the geometry or the shape of something, I'm picking out a central atom, so the middle atom of the molecule, and I'm looking what's around it. How many electron domains are there? And there's two types of electron domains. There's the bonding domains, okay? And there's lone pair domains or unshared pair, okay? Now, let's understand that a single bond counts as one bonding domain. A double bond counts as one bonding domain. So yes, a double bond is 4 electrons being shared, and whatever atoms over here and whatever atoms over here, it would be 4 electrons for this atom and 4 electrons for that atom. But if I'm trying to figure out shape, if I'm trying to figure out hybridization, which we'll talk about later, I see a double bond and I know that's one domain. So one, and to be more specific, one bonding domain. And then also the same thing with a triple bond. Yes, it's 6 electrons being shared, but it still just counts as one bonding domain. And then anytime you have a lone pair, and very rarely you might just have a single electron by itself, that would count as one domain. And it would be a lone pair domain, even though it's really not a pair. But most of the time you're dealing with 2 dots not being shared. That's why sometimes it's called an unshared pair. That would be one domain, okay? So if I ask you about the geometry around a certain atom or of a molecule, all you care about, for geometry, all you care about is total domains. You don't care about differentiating the types, okay? Is it a bonding domain or is it a lone pair domain? When you're trying to figure out the shape, that's when you have to know which types of domains you have. You have to know how many you have total, but you have to distinguish between bonding domains and lone pairs, okay? So for geometry, there's just these geometries. There's linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. So if I have 2 total domains, I'm linear. If I have 3 in terms of VSEPR theory geometry. So 2 domains, linear, 3 domains, trigonal planar, 4 domains, tetrahedral, 5 domains, trigonal bipyramidal, 6 domains, octahedral. All right, that's my geometry. Okay, now within the geometries, we have different shapes. And the shapes are, okay, well, I might have 4 domains, but how many are bond domains and how many are lone pairs? And that'll tell me what shape I have. Okay, but like methane has 4 domains, but they're 4 bonds. Water has 4 domains, but it's 2 bonds and 2 lone pairs. So they would both technically be tetrahedral geometry, but if I ask you the shape of methane, you would say tetrahedral, and if I asked you the shape of water, you would say bent. Okay, even though they're tetrahedral geometry. So shape is a subgroup of geometry. Okay? Now, here's the deal. When the domains here are all bonds, so if I have 6 bonding domains, if I have 5 bonding domains, if I have 4 bonding domains, if I have 3 bonding domains, if I have 2 bonding domains, if the domains are all bonding domains, then the geometry and the shape are the same thing. So something with 2 bonding domains and that's it is going to be linear in terms of shape and geometry. Something with 5 bonding domains and 5 total domains is going to be called trigonal bipyramidal geometry, and it would also be called trigonal bipyramidal shape. And I'm going to show you a chart here. Hopefully that makes sense. But when all the domains are bonding domains, that's when shape and geometry are the same thing. Okay? Same name. All right? So when it comes down to shape, we need to not only know how many domains we have, but we got to know what types we have. You know, how many of the domains around the atom are bonding domains and how many domains are electron pairs, okay, or unshared pairs. So for linear, there is no subcategory of shape. If you have 2 domains, it doesn't matter if it's 2 bonds and 0 lone pairs or 1 bond and 1 lone pair, it's linear, okay? But now if we have 3 domains, we could have 3 total bonds, and if we have 3 bonding domains, if my 3 domains are 3 bonding domains, my shape is trigonal planar. But now, under this geometry, trigonal planar, 3 total domains, if 2 of them are bonding domains and 1 is a lone pair, the shape is called bent, but sometimes called angular, because there's 2 actual times where you're bent. So you can call this one angular, okay? So when you get to 4 domains, we have 3 different shapes. We have tetrahedral when all the domains are 4 bonding domains. When I have 3 bonds and 1 lone pair, we call that trigonal pyramidal, not trigonal bipyramidal, trigonal pyramidal. And like water, when I have 2 bonds and 2 lone pairs around my atom, we call that shape bent. It's tetrahedral geometry, but if that's my combination of my 4 domains, it's bent shape. Okay. So 5 domains, we have a little bit more, right? So if we have 5 bonding domains, it's the same as the geometry, trigonal bipyramidal shape. But now if I have 4 bonds and 1 lone pair instead, that's when we call that seesaw. If I have 3 bonds and 2 lone pairs, that's where we get this shape called T-shaped. It's still, again, the geometry is trigonal bipyramidal because it's 5 total domains. But if that's your combination of domains, the shape is called T-shape. And then we get linear again, and that's when you have 2 bonds and 3 lone pairs. And this hopefully will make more sense when we break out the model kits. But the shape, it's trigonal bipyramidal geometry, but the shape actually ends up being linear. Okay. And then when we get 6 domains, obviously the 6 bonds is octahedral. 5 bonds and 1 lone pair, that's where we get the square pyramidal shape. 4 bonds and 2 lone pairs, that's where we get the square planar shape. And then there's other shapes too, like if I said 3 bonds and 3 domains, then we're back to bent again. It's just bent with a smaller bond angle. But these are all kind of the unique ones. Okay. So here's a chart that kind of shows you what I'm saying. So instead of them calling it the geometry, they're calling it the parent shape. So when you have 2 domains, you're linear. When you have 3 domains, you're trigonal planar. Okay. But and here's like bonding domains and lone pair domains. If the geometry is trigonal planar, or the parent shape, If it's 3-0, the shape is called trigonal planar. If it's 2-1, two bonds, one lone pair, it's bent or angular. Okay, and then here's some bond angles to reference. Okay, so tetrahedral. We call it tetrahedral shape when it's 4 bonds, 0 lone pairs. When it's 3 bonds, 1 lone pair, it's still tetrahedral geometry, but trigonal pyramidal shape. And then 2 and 2, we got bent. And notice the bond angles go from like 109 to 107 to 104. It's really like 109.5, 107, 104.5. A lot of times I'll just tell you to go 109, 107, 105, just subtract 2. But really, if you're asked for a bond angle, they always allow leeway. So when it comes down to bond angle, you don't care tetrahedral, trigonal pyramidal, bent. You just care 4 domains. I'm just going to say 109. Okay, but anyway, here's the rest of the chart. So trigonal bipyramidal geometry, right? If there are 5 bonds, 0 lone pairs, then it's trigonal bipyramidal shape. But if it's 4-1, then it's seesaw shape, 3-2, T-shaped, 2-3, linear, and we can keep going. Okay. So.
Back, sir.
Okay, so if we look at this molecule here, PCl5, right? We draw its dot structure. We have 5 bonds, okay, and we have 5. So we have 5 total domains around the phosphorus atom, and only 5 domains. All right, so we got 5 domains, and they're all bonds. So 5 domains, the geometry is trigonal bipyramidal, but if they're, and if all 5 are bonds, the shape is also trigonal bipyramidal. So here's an example. I have the SF4 molecule. I still have 5 total domains, so the geometry is trigonal bipyramidal. But now the ratio, I have 4 of those domains are bonds, and 1 is an unshared pair. So that's why the shape is called seesaw. So it's still the same geometry as this molecule, but the molecular shape is different. Okay.